states should be, right? And I told you what the little groups are and what the representations are, right? And then you went on to go through this whole Lagrangian derivation and everything. But really what all this thing is just reproducing the state counting here by deriving the equation of motion, where the equation of motion allows you to derive, to force that these function corresponds to the representations of your little, that you have the correct degrees of freedom. Okay, 所以这是我一个非常，既然你们已经学过一整学期的场论了，所以我希望你们能够知道说这个可以fully appreciate 说这个 statement， 就是你的 degrees of freedom， 事实上你只要一旦知道你的 symmetry 知道在这我们的 case little group 的话，你就已经知道 degree of freedom 是在做什么。那现在问题是说，你现在 somehow 要用一种方法，特别的方法去算一些 process 的话，那你就首先你在处理这个方法的时候，任何时候你要 develop， 今天这搞不好不会是你 prefer， 你可能想要走完全自己的路，你可以去 develop 你自己的方法，没问题。但你在 develop 你自己的方法的时候，你要先做的第一件事情就是你要先 reproduce 这个 correct degrees of freedom， 对吧？那在这个 part2 的 formula 这个你的 correct degree of freedom 是怎么出来的？是从你 equation motion 出来，对不对？因为它 encode 说它有个 h bar 在这边可以让你 connect between classical 跟 quantum。那所以一旦在 h bar 很小的时候，你有 equation motion， 这时候你就可以得到一堆 equation motion。你去 solve 这些 equation motion 的时候，就必须要能够，它是借由说 solve 这些 equation motion 来给你说这个，给你说那个 correct state count， 透过 equation motion 出来。OK， 那上学期最后你们真正学到的最后就是得到这些 equation motion， 对吧？所以我就说你们上学期在做的事情就是在知道 state 是哪些。这样够 clear 吗 ？equation motion 是在告诉你的 state 有哪些。OK。Of course, equation motion. 当我说 equation motion 是这样之后，我们在讨论是 free theory 的 equation motion， 对吧？ When we're talking about equation motion, and I just listed these three, it just means that I was looking at the free theory. Now, in principle, we know that in general, the Lagrangian here will contain more than just this, right? It will contain, so for example, for the scalar theory, our Lagrangian can be equal to 1/2 phi box phi, for example, plus let's just say, for example, lambda phi cubed. Yeah, right? And for the equation motion, without the equation motion of this, would give you box phi plus 3 lambda phi squared, right, equals 0. So you'll say, oh, wait a minute, but this is not this. This is more complicated. But the point is that lambda is a small parameter, right? So at the first order, if you solve this equation at first order, this is always box phi equals 0. And that defines the states that you're working with, okay? And the higher order terms here are just telling you what the interactions look like. Okay. Good. So I hope that I persuaded you that last semester was mostly describing just what the states are. Now, more importantly, last semester, QFT1. Okay, so let me just erase this. So more importantly, last semester, QFT1 was completely classical. So you spend the entire semester doing 0 quantum physics. So this is what I want to, this is another thing I want to stress. What you've done last semester is completely classical. There's no quantum in what you did last semester. Okay? I mean, obviously, as I just said before, the reason that you were looking at these equation of motions was because you're looking at you're looking at h bar very small. You're looking at the saddle point, right? That by itself should tell you that you're looking at classical, right? These are the states that are essentially defined classically. So even though, so this is the other reason I wanted to stress this, that saying that you have an operator acting on a vacuum create plane wave, that is not really what, I mean, that's a formalism statement. That doesn't really do, because you have this false notion that, oh, you know, you start with harmonic oscillators and you have multiple harmonics, you excite the vacuum, and so you have this discussion. You're doing something quantum. But no, there's nothing quantum in it. And to persuade you, let's just consider an observable. Okay, so let's just start with, again, last semester, so let's just start again with the simplest theory, which is just the scalar theory with lambda pi cube. Okay, so what does classical mean? What does classical and quantum really mean? It's very simple, right? It just means that you have a parameter that is h bar and you're expanding it in small h bar. The leading term is classical, all the remaining term is quantum. Everybody agrees? 古典跟量子的差别是什么？很简单，就你有个 h bar， 对不对？你再做一个围绕，用 h bar 去做围绕，第一项是古典的结果，所有后面的修正项就是量子效应。这就是对不对？大家同意吗？我对我这个 statement， 对吗 ？Okay. All right. Good. So let's just consider a process. So let's just consider, for example, this scattering process. Now, the way that you would compute this in last semester in Hamiltonian formulas is you would write down the interacting vertexes in this oscillator, and then you would move things around, right? Jumping over, hitting the vacuum, what vanish, and you get something in the end, right? You think that you're doing something quantum, but no, you're actually just doing a classical computation in a very difficult way. Because there's nothing quantum in it. And to see why, it's very simple. So let's say if you want to compute this from here. So what does this entail? From last semester, you know that you can compute this process from a Feynman diagram, right? What you do is you take the vertex here, and a vertex here, an imaginary vertex here, and then you just connect it with the propagator, D12, right? The precision space propagator will be D12, right? I think you're all familiar with this notation because this was actually in the midterm last semester, right? Okay, now let's just put in h bar. So remember that this was sitting in front of a dx4 with a 1 over h bar. So that means that this vertex here has a 1 over h bar. This vertex here has a 1 over h bar. And here, this has an h bar. Do you agree? Do you agree that these vertex has 1 over h bar? The people who are confident and agree, can you raise your hand? 同意这两个的 factor 是 h bar 的举手。OK， 大家并不是很清楚，原因很简，sorry， 这两个 vertex 是 1 over h bar， 同意的举手。OK， 好，有些人不是很清楚，因为答案很简单，我只是把这 h bar 填进来，这边有 1 over h bar， 这边有 1 over h bar。所以这个 phi q 不是在每一个 phi q 在这边不是出现1 over h bar 吗？对不对？这样可以接受吗 ？Okay. The reason that these have a 1 over h bar is just because I'm just multiplying this 1 over h bar in. So each factor carries a 1 over h bar. Okay, that's simple. Propagator is h bar. If you agree with that, raise your hand. Okay, some people don't know why the propagator has an h bar. Do you remember what the propagator is? The propagator is defined, or this D12 is defined by the Green's function. It's called what we call the Green's function, right? How was it defined? It was defined by the statement that D12 should satisfy box acting on D12 as delta. X1 minus X2. Remember? It was defined by this equation, right? Why do we define the Green's function using this equation? Because we're doing the variation of this two phi's, right? If I'm putting in the h bar, that means I'm putting in an h bar here, right? Because this is a 1 over h bar. I should really have a 1 over h bar here, right? So that means that D12, even when you solve it, this actually contains an h bar here. You should put in an h bar. Okay, because the propagator is the inverse of your quadratic operator, right? So there should be a h bar here. Okay, so the total counting of this diagram is 1 over h bar. Now when h bar goes to 0, what happens? This diverges. So what does that mean? That means this is a classical part. Okay. That means what you've just computed using you can use harmonic oscillator all you want. You can compute this complicated thing, but after doing all that, you're just computing something that is classical. 1 over h bar. Okay, you can consider more complicated diagram. So, oh, maybe you're brave enough and you can try to compute this, but still, this is 1 over h bar, this is 1 over h bar, this is 1 over h bar, and this is h bar because there's a propagator here, and this is h bar here. The total is still 1 over h bar. You're still doing something that is classical. Okay? So even though you learned all this machinery last semester, this makes you sound very cool, or it makes the course sound very cool, quantum field theory 1. There was actually 0 things that was quantum. Everything that we've computed, that we've tried so far in last semester, you're just doing something that is classical. Now you can think about what would be a quantum thing. Now we can try to draw diagrams here, and it turns out that this diagram, for example, would be a quantum effect, right? Because now we can just count. There's 1, 2, 3, 4 vertex. So this is 1 over h bar to the 4th. And then I have 1, 2, 3, 4. And then this is h bar to the 4th. Ah, now I have something that which is h bar to the 0. So this is the first correction in the h bar expansion. Right? So this is the true quantum effect. Okay? So that's the point of this semester, to put back the quantum. Okay, so in this semester, what we're going to talk about really what happens at the quantum level, the quantum effect. Okay, so last semester, so as a review, last semester what did we learn? You learned how to define states, what are the proper way to describe the states, how to derive a state from one particle states from the path integral formalism. We know that the one particle states you have different spins, and how do you derive it from the Lagrangian formalism. And we try to introduce interactions, and we computed some interactions, but the point is everything that we computed and did in last semester was all classical. And this semester we're going to start doing with the quantum. Okay, so that's really, so in other words, last semester instead of QFT1, we should probably just say CFT, sorry, not CFT, it's just classical field theory. Okay, last semester is really just classical. And that is really what I want to stress here, because it's not, whether things are quantum or not does not depend on how you do things. Okay, so it doesn't mean that just because you're using oscillator algebra, you're using harmonic oscillator, that means you're doing something quantum. No, you can use harmonic oscillator and just do classical things, which is precisely what we did last semester. Okay, so to keep track of whatever things are quantum, you need to keep track where the h bars are. Okay, so that's what I wanted to say. Good. So this should be sufficient review of what we did last semester. So this semester, we're going to do quantum. So this semester, we're going to do quantum. So again, so let's just, if we start with the path integral formulation. In that diagrammatic expansion, we can show that in general, any observable, you would have a tree part, a one loop part, for example, a two loop part, and so on and so forth. You can compute it from this, or you can also compute correlation functions. Correlation function as well. You can have two operators here, and then this will be the tree part plus, for example, the one loop part, where you have this, and the two loop part. You have this. Okay, so but in general, anything that you compute, auto-observable, you can compute has an expansion in terms of h bar. Now here, we know that, previously we know that this is essentially the 1 over h bar here, this is h bar to the 0, and this is h bar to the 1, and then this will be up to 1 over h bar to the square. But there's an infinite expansion, okay, in terms of h bars. This is the classical piece, and everything here are the quantum piece. Okay? good. So now we're going to think about what these pieces are going to tell us. So what can we expect? Or what kind of questions can you ask? And then I'm going to tell you what can you expect. So what can we expect from all these corrections? Okay. First of all, symmetries will be broken. Okay? Just because you have something in your Lagrangian that respects certain symmetry, that doesn't mean that the quantum effects can preserve the symmetry. And there's various ways of saying this. One of the simplest way is just to say that even though your Lagrangian has a symmetry, it doesn't mean that your measure has the same symmetry, because now you're summing over all the measures. Okay? Or another way of saying it is just because when you're doing the computation of these quantum corrections, you generically will need a regulator. And that regulator may break your symmetry. I'll talk this way of saying things, it'll come up in 5 minutes. Okay, but basically, we can expect that certain symmetry can be broken by these quantum corrections. Okay. Second, it's really that the scale dependence will emerge. Okay. Why do I say that scale dependence will start to emerge? Let's see what happens. Let's just take this simple diagram and see what happens. So let's take this simple diagram. And you already know you want to do Feynman rules, right? You already know how to do Feynman rules, right? So you know that there's 4 vertex here. So if you want to compute this diagram, you have the 4, but these are just 5, 4. So this is just lambda to the 4 because you have 4 vertex. So let me just label 1, 2, 3, 4. So you have a propagator here, right? A propagator here, and a propagator here, and a propagator here. So let me just call this big P1, this is big P2, this is P3, and this is P4. Okay, I'm going to write these propagators. Okay? So the answer is just going to be 1 over P1 squared, 1 over P2 squared, 1 over P3 squared, and 1 over P4 squared. Right? This is your answer. Everybody agree? Those who agree, raise your hand. 你同意的举手。我现在要算这个东西，我现在就说你现在有这四个 vertex 嘛，所以就有4个 lambda， 对不对？那你现在是要用它的 propagator 把它写下来，把它的 propagator 全部乘在一起，对吧？这没什么，对，这就是我们上学有学过。All right. But this answer means 0 sense, right? Because I have to tell you what P1, P2, P3, P4 is, right? Good. So let's say this is the momentum K. Let me just use this to represent momentum. This is called K2, K1, K3, and K4. Okay? Good. So then, what is P1? Because momentum conservation is happening at each vertex, right? So that means that P1 is going to be equal to 1 over K1 plus K2 squared. P2 is going to be 1 over K2 plus, K3 plus K4 squared. Let's say the particles are masses. Anybody disagree with these two? 大家都同意吗？可以吗？好。Good. 现在问题来了。P3 跟 P4 的 momentum 应该什么？ What is the momentum for P3 and P4? So you see, once you have a loop, then you have a problem because once you have a loop, the momentum inside the loop is not fixed by the momentum conservation. In fact, I can now just write down, so let's say the momentum is flowing here and here. So let's say the momentum P3 is, let me just call it P3 squared. And this momentum P4 now, because of momentum conservation, is just going to be P3 minus P2 squared. just by saying this is P3 and P4 equals P3 minus P2, all momentum conservation are solved. Do you agree? 对不对？我只要把 P4 写成 P3 减掉 P2 的话，所有点的 momentum conservation 都解了。大家可以接受吗？对不对？因为这个 momentum conservation 告诉你 P1 等于 K1 加 K2，这个 momentum conservation 告诉你 P3， 对不对 ？P3 出来跟 P4 进去，所以 P4 假设说这边是进来的话，这个 momentum conservation 会告诉你的是说，你 P4 加 P1 要等于 P3嘛，对不对？可是你这边已经说了 P4 实际上等于 P3减 P2， 所以说 P4 实际上是这边的 P4 的话，这个你可以把它写成 P3减 P2 加 P1， 对吧？因为我现在用 P4等于 P3减 P2， 对吧？那这个是不是 obviously P3 就会相消嘛？那 P2 跟 P1 因为这两个是这边有多少 momentum， 既然这边有 momentum 出去，所以这也会相消，这 obviously satisfied。所以这 momentum conservation 也被 satisfy， 这个 momentum conservation 也被 satisfy。OK， 所以 momentum conservation 告诉你说，你最后这些 propagator 长得是这样的形式。这个 P2 我还可以把它写一下，因为我刚刚说过 P2 上是等于 K3 加 K4， 所以这个是 K3 加 K4。Okay, so you see that this is something new that happens at loop level. And that is that all the momentum in your graph is not completely fixed by the momentum delta functions. Here, P3 can be anything. Okay, 这是跟 classical 的地方不一样，而且这才是真正 precisely 为什么会有 quantum effect. Okay, 在 classical 的时候 when you're looking at a classical diagram, no matter how complicated the diagram is, okay, I can just draw some arbitrary complicated diagram. Whenever I have this diagram, if there's no loop in it, then that means that once I know the momentum of the external legs, all the propagators inside are known. All the momentum inside are known. It's just fixed by the momentum conservation. Okay? But whenever you have a loop here, then the momentum, there's going to be one momentum per loop that is not going to be fixed by momentum delta. Okay? And so what is the prescription? Then this means that this can be anything. So that means you need to do an integral. You need to sum over all possible momentum inside. Okay? So whenever we have quantum corrections, that means that you always have loop. Okay? And whenever you have loop, that means you're going to have unfixed momentum. And that means the momentum can be anything. You need to integrate over. Okay? And this is why you have scale difference. Now you need to discuss scale dependence. Why? When we're writing down a Lagrangian, this is not just some mathematical object. Remember, even though there's a lot of beauty in Lagrangian or a lot of beauty in gauge symmetry, so on and so forth, there's a lot of beauty in the mathematical structure, but really this is not just a math object. This is something that you're describing the physical system, right? Whenever you're describing a physical system, you're always sitting at some scale, some energy scale, right? When we're discussing the interaction of neutrons, right? The interaction of protons. You're at the energy scale where QCD or quark or gluon, they're completely irrelevant. Right? When you're talking about molecules, you're at an energy scale where the atomic structure where the nuclear structure is completely irrelevant. Right? You don't see the physics of that scale. Right? So whenever we're describing a system, we're always sitting at some scales to describe and discussing the system at some scale. Right? So that means that when you're writing down this Lagrangian, even though it's an object, if you really want to use this Lagrangian to describe physics, then you're actually secretly letting this you're using this Lagrangian and you're saying that this is describing physics at a particular scale. Okay? That's fine, there's nothing wrong with that. But here comes the problem. Even if you're describing physics at a particular scale, but whenever you start having quantum level corrections, you're introducing an effect where this momentum will integrate over all momentum, meaning that it integrates over all scale. Right? So that means that this will now, even though you're starting with something at a particular scale, in your computation you will be sensitive to whatever happened in high energy because of this momentum. So now your theory becomes very sensitive to the scale, to the scale dependency of the underlying theory because of this momentum here, this momentum here. Okay, and this is basically, you can already expect that just by using what you know at tree level, and you try to construct some physical, and then you realize you need to integrate all possible. Then you become very worried, right? For example, let's say if you're trying to do, if you're going to some research group in nuclear physics, right? And now you want to describe, you have some Lagrangian, and you're trying to, I want to use Lagrangian. Let's say I want to use Lagrangian to compute the interaction of 4 protons, right? You want to go proton, 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 proton. And your professor tells you, you have to be, or your classmate, the professor won't say that, but your classmate will say, you're doing proton, why don't you just do QCD? Or why don't you consider quark and gluons and stuff? You say, I don't need to care about that, because I'm just thinking about protons interacting, and the proton is interacting as very low energies, so that you don't actually go into high energy and touch these issues about being quarks. They're actually not protons, but they're actually quarks. Let's say you say that. But then you say, but I'm considering these proton-proton scattering. I want to consider quantum effect. Now your classmate can be very suspicious of you. Because when you're saying quantum effect, that means you're doing this. And that means you're introducing these integrals. So these integrals can be arbitrarily large. Right? So even though the outside momentum are very small compared to the scale that sitting at the scale that you're discussing, inside, you have no control over what's going on inside. And these can be arbitrarily high. And these will be sensitive to whatever is happening in the ultraviolet, in the okay. So, in other words, let me just say this in layman's sense. When we're not talking about quantum corrections, when we're just talking about this, you can talk about any scale you want. There's no urgency introducing or to really appreciate which scale you're in. But once you start doing quantum effects, now you need to be, your discussion is going to be very sensitive to the scale dependence. Okay? And it's precisely because of this integral sitting here. Everybody's okay with that? All right. Now that you see that you have these integral, that means that you have a third thing to worry about, which is what happens when divergences. Okay, why? It's very simple, right? Because your integral, this can go to infinity. Right? Anything that you're integrating to infinity, you might have divergences. And also, since this integral, we also integrate near 0, you can also have divergences near 0. Right? So for example, what are divergences you need to worry about? You need to worry about polynomial divergence. For example, if you're integrating 0 to infinity, this will be a divergence, right? So these are what we call polynomial divergence. And then, for example, we have over x 0 to infinity, this will be a log divergence. And if we have anything more that is more than x to the a, where a is bigger than 1, then these are no longer log divergence. We usually call these infrared divergence. So this is called ultraviolet.